Yeah, you can give your attendances now. By the way, any questions from previous lectures?
Sir, I have few questions.
Yes.
Sir, in the Goldstein's book, it is written that if Lagrangian is quadratic or function of q dot only and constant, then we can write the Hamiltonian just t plus v. And it is mentioned that you can prove it, but I'm not able to get that thing out. What is the meaning of this thing?
Mm, what do you mean? What is the meaning of this thing? I mean, what meaning are you looking for?
Sir, it is said that if Lagrangian can be written as L naught, which is function of q dot qi and t, and L1, which is function of qi and t times q dot k, and L2, that is function of qi and t multiplied by qk dot and qm dot.
Okay.
Then it is written that if L2 is just have no time dependent, then we can simply write it as the uh, kinetic energy of the system and L naught as the potential energy. But I did not get that how they cancel out this L1 Q T term, which is times Q dot K.
Uh, I think that is because if that is linear, then when you try to construct the Hamiltonian, that thing will cancel from PIQI dot. So it's PIQI dot minus L, so that piece might get cancelled.
No, sir, in calculating that PI, it contains three terms with L, DLL, del QI dot, and then there for L2 there are other two.
Okay, then I'm not sure I quite follow that thing. I have to check on the details.
It's on 8 chapter 8 equation 8.20.
Okay, I have to check.
Okay, sir.
Anything else?
Okay, sir, the next thing is, sir, in canonical transformation, we have to, it not like just point transformation, right? I have to
It is not point
define,
transformation.
okay. Then,
It
sir, what you are trying to prove in that infinitesimal canonical transform?
is basically general canonical transformation, the infinitesimal version of that. In so that we change the phase space coordinates by an infinitesimal amount. So we are very close to the original points. If you look at the time evolution of the thing, then that means that uh, you are very close to the t equals to 0 frame. Okay. Okay, I have not shared the screen, I guess. Um,
Then, in that, after had applying that infinitesimal canonical transform, are we trying to get the conserved quantities out just like we did in the case of Noether's theorem?
uh, the essential point of canonical transformation is this. So suppose let us start with at t equals 0. Okay, you had your coordinates and moment as q0 and p0, and at time t you have qt and pt. Okay. Now if I ask you this, okay, suppose at t equals to 0, your q and p satisfied this, right? Or let's say 1,
Yes, sir.
and q equals to 0. Then can you tell me what is the guarantee that at time t it will also satisfy this thing?
Yes, sir.
Who tells you that?
Mm.
So that means the evolution of this will preserve this fundamental Poisson bracket relation if the evolution is canonical, or from you come from q0 to qt or p0 to pt in a way that resembles a canonical transformation. So that is essentially what is meant by canonical transformation. So canonical transformation basically means you redefine your phase space coordinates in many different ways, and your Hamilton's equation still holds in those things, or rather Poisson bracket relation holds in terms of those coordinates. So canonical transformation is essentially the condition for that to happen.
Okay, sir.
Okay, and
Good.
infinitesimal means basically this t is tends to 0. So you are looking at like infinitesimal time after the initial condition. Okay,
Mm.
anything else?
No, sir.
All right, anyone else have any other question? So in last lecture, probably we have found the Heisenberg equation of motion, which is if you are given say f as a function of q and p such that so df dt turns out to be the Poisson bracket between f and h. And we've found that if uh, f and h commutes, then f is a conserved quantity. So if a system has any conserved quantity, the easy way to check that would be whether that quantity commutes or Poisson commutes with the Hamiltonian. Now, suppose you have found two such conserved quantities, let's say f and g, such that let's say uh, f h and let's say g h, both of them are 0, and then these two are conserved quantities, of course, and then you can check that you define, let's say, small h, which is the Poisson bracket between f and g. Okay, you can check that this Poisson bracket is also 0. So if f and g are conserved quantities, then f commutated g is also a conserved quantity. So you kind of created a new conserved quantity here. So you started from f and g, you assume these two are my conserved quantities, and then you found that this thing h is also a conserved quantity. So you can prove this by employing Jacobi's identity. Now you might wonder, so in this way can I like keep on finding infinite number of conserved quantities, because now I have found h. Okay, so I can try to write down, let's say, h prime, which is h commutator f. Okay, but if you do that, you should just get back g. Okay, so the point is, just by applying this trick, you cannot try and create infinite number of conserved quantities. So in this sense, it is said that if f and g are conserved, let's say f and g are conserved, then you can probably find one more conserved quantity, that is f commutated g, and these three things form a closed algebra under the Poisson bracket relation. So you would be saying that, say, f, g, and h, uh, so they constitute a closed algebra under Poisson bracket. Okay. So this is the first lesson that you learn. Okay. Now there is a homework problem. So how do I see these kind of things? There is a homework problem in your homework number 5. So you should do that. So what I did is that I defined the angular momentum as r cross p. Okay. So that means you can write down the components of the angular momentum. So suppose L1, which is the, say, Lx, so that would be x2 p3 minus x3 p2, and so on and so forth. And you can check that this satisfies the Poisson-Bracket relation that is given by LA LB is equals epsilon ABC LC. You have to do that thing, so then you can find it out. Okay, and you also, so you can use this to write basically L1 L2 is equals L3. Okay, so this basically tells you if in under Hamiltonian or under a particular evolution of a system, L1 and L2 are conserved. Suppose these two are conserved, then the third component is also conserved because of this, right? Because if L1 and L2 are conserved quantities, then the Poisson bracket between them is also a conserved quantity. That means the whole L is conserved. All of these three components are conserved. So this means these are conserved. The whole L vector is conserved. Yeah. So, so basically, one example of closed Poisson bracket algebra, you can check that L1, L2, and L3 form closed algebra under Poisson bracket relation. Okay, and you can also check that if you take the Poisson bracket between L square and any of the component of L, you should find out to be 0. Okay, so these are all familiar to you from quantum mechanics. So these are the essential things that happens in quantum mechanics. One interesting side note is that what happens for central potential in central potential, in particular the 1 by r attractive potential. So for such potential, you can construct a quantity called the Runge-Lenge vector, or sometimes it's called the Laplace Runge-Lenge vector. Okay. So this vector is given by, so V is equals 1 by m, then P cross L minus r cap. Okay, so r cap is the unit vector along r, and so you can easily check that this vector satisfies V dot L equals 0. Okay. Now there was another homework for you to check that these Poisson-Bracket relations hold. So if you find out LAVB, you should find summation over C epsilon ABC VC. Okay, and you can check that VA VB is equals to minus of 2 by m p square by twice m minus 1 by r summation over C epsilon ABC LC. Okay. So this, the second Poisson bracket relation gives you one very interesting implication to this. So the idea is what happens if the Hamiltonian has this structure. So suppose your Hamiltonian is this. So Hamiltonian is your p square over twice m minus 1 by r. This is a very familiar looking Hamiltonian to you. So if you, so this is basically the Hamiltonian for an hydrogen atom or an attractive gravitational field, things like that. Okay. So, so if this is your Hamiltonian, then you can write that VA VB is equals minus 2 times the Hamiltonian over m times summation over C epsilon A B C LC. Great. Now again, so if this is the case, then it will follow from here that you can check now that for this Hamiltonian HV, the Poisson bracket between H and V is equals to 0. That means, or I should put a vector here, any of the component commutes with this thing. So that means that V is also a conserved quantity. So V is also a conserved quantity. Okay. Now this has a very deep implication actually. So I initiated this this discussion for some reason. Anyway, sorry. I will come to that. But before that, if V is a constant conserved quantity, and I already know that for central force problems, L is also conserved. So basically, you can check that HL is equals to 0 for any conservative, for any central potential. So this happens for any central potential. Okay. H commutator L equals 0. So now you can go back to the expression of this V. So V, remember, so V is equals 1 by M P dot L minus R. So V is equals 1 by M P cross L minus R. Okay. So suppose you dot it with R cap. Okay. So you take the dot product of this whole equation with R cap. Okay. And remember, for 1 by R potential or attractive 1 by R potential, both this V and this L are constant. So these are two constant vectors pointing in space in a constant direction. So if a vector is constant, that means both its magnitude and its direction is constant. Okay. All right. So let me denote the magnitude of V as epsilon. So magnitude of V I denote by epsilon for intentionally. Okay. So then V dot R is basically epsilon cosine theta equals 1 by M. This is P cross L dot R, right? Now again, you can rearrange this thing to write down. So this R vector you write as R by R, and then this is minus 1. Okay. So you have to rearrange this thing. So this vector triple product you can write as 1 by MR. So P cross L dot R, perhaps you can write it as L dot R cross P, right? Yeah, it looks okay. Yes. So this is like this is again L. Okay, and this is then L square over MR. So this is L square over MR minus 1. Okay. Now, if you rearrange this thing, so remember this L has a constant magnitude again. So this L square I write it as small L square. So basically I write as small L by R equals 1 plus epsilon cosine theta. Okay. Now this small L is basically a shorthand for this constant, which is L square over M. Okay. So that is just my notation. Okay. This is my small L over R equals 1 plus epsilon cos theta. Perhaps you remember this equation from your undergraduate days. So this is the equation of a conic section. Okay. and particularly if epsilon less than 1, then it is an ellipse. So that is the reason why if you study the motion of a particle under an attractive 1 by r potential, the equation of the orbit turns out to be a conic section, in particular that is of an ellipse. Okay, so using Laplace Runge-Lensing vector, your calculation becomes simple, and but there is more. The second puzzle I want to explain is a puzzle again from quantum mechanics. So the question is that perhaps you remember that for an hydrogen atom problem, okay, if you kind of try to find the bound state energies, then the bound state energy only depends on the principal quantum number n, and it is proportional to 1 by n square, perhaps with a minus sign. So there is no dependence on L. Okay. So so you know that for a central potential, so if you have a central potential, okay, then perhaps you have heard that it contains an azimuthal symmetry, that is a rotational symmetry around phi. Okay, so that means this Lz is conserved. I mean, you take the conserved direction along the z direction, it is conserved, and that's why the energy eigenvalues are independent of m. Okay, so energy eigenvalues are independent of this quantum number called m. Okay, but why is the energy eigenvalues are independent of L? Okay, so my question is why E doesn't depend on L? Okay. So the answer lies here actually. By the way, have you solved any other Schrodinger equation apart from the hydrogen atom, and did you notice on what quantum numbers do your energy eigenvalues depend? Any three-dimensional problem, any other three-dimensional problem have you done other than the hydrogen atom?
Isotropic harmonic oscillator.
Yes, sir.
Okay, so what does it depend on?
P quantum.
Only n. Proportional to n.
For
Also,
isotropic harmonic oscillator, it depends on only n.
no, sir. N1,
Yes,
N2,
means n plus
N3.
3 by 2. H cut omega. So it
No,
basically
no, no,
means
no, no, no. I'm talking about solving it in three dimension. Actually, it depends on three
Yes, sir. 3.
quantum number n1, n2,
N1,
n3.
N2, N3.
Yeah,
yes,
it's
yes.
not n. Okay, but in three dimension, if you do the version of three dimension, then like sorry, by three dimension I mean the three dimension spherical polar coordinate. So the radial equation, if you solve, do you know how the radial equation looks like?
Yes,
Sir,
sir.
it will
Like
depend
the
on
Schrodinger equation.
N and L, sir, for helium atom.
Yes, but helium atom you do not solve exactly. You use perturbation theory, perhaps.
Yes, sir.
Yeah, but anything that you have solved exactly, let's say free particle,
Particle in a box.
that doesn't have a spherical symmetry. I'm talking about anyway. Let me try to give you a hint here. So the radial Schrodinger equation for central potential look like this. So d2u dr2 plus I think it has the structure like this, L into, I am missing out the factors of H cross and M. And this type of things equals to 0. Okay. Have you ever seen this equation? This is a radial equation. Okay. And so this is usually called the centrifugal term. That has the effect of kind of effectively reducing your potential.
Sir, is there minus sign or plus sign before this L into L plus 1 by R square term?
I think that is a minus sign, but maybe there is a plus sign, but that is not the important point here. But there is
Okay,
an L dependence. Okay.
okay,
But
sir.
I think the sign is minus, but maybe I am wrong here also. So you should check that. Okay. So the thing is that then the radial, so you get your energy eigenvalues by solving this equation, actually. So the radial equation, the solution of radial equation, and it depends on your this constant L that denote your angular momentum, right? But then something happens if your VR is in particular of the structure of minus 1 by R, then something special happens, and you see that at the end when you calculate your energy eigenvalues, the L dependence goes away. Okay? So now I want to ask you why that happens actually. Okay. I think if you have solved this equation for free particle, let's say, so Vr equals to 0, okay, and you will find this Bessel's equation. So this then resembles to the Bessel's equation, the spherical Bessel's equation, and it depends on this thing K and L. So K is the energy essentially, and L. Have you done this thing, the spherical Bessel functions? A function like, let's say, JLKR, something like that? No.
Yes.
Okay. You'd have done it?
Yes, sir.
Okay. Good. So, and it depends on this L, right? You have noticed this all important L here. Yeah. And the energies will also depend on this L. So, in general, if VR is an arbitrary central potential, then your energy eigenvalues will depend on N as well as on L. But something very special happens when the potential is of the structure minus 1 upon R. Okay. And it is on for those cases that your energy eigenvalues do not depend on N. Okay. So if you try to understand why is that, okay. So it happens again with the symmetry. So in the last class, I perhaps mentioned that if a Hamiltonian has a symmetry under something, then the Hamiltonian commutes with the generator of that symmetry. Okay, so it goes like this. So you have this thing. Say you have S H S dagger equals H. If S is a symmetry operation, and you multiply this with S from the right, and you get SH equals HS, and that gives you S commutator H equals 0. Okay, so that gives you S to be a conserved quantity. But the things that happen is that if this occurs, if this type of relations hold, then usually you will find that your Hamiltonian has degenerate eigenstates, and those degeneracies will be broken by the labelings of this S. Let me give you an example. So that is the thing that so if this is the relation, then H has degenerate eigenstates and different degenerate eigenstates, are labeled by the eigen values of S. Okay. So again, to give you an example from the last class, I told you, suppose H is your identity matrix, 2 cross 2 identity matrix. Then you find out that you cannot find the eigenvector. Okay. So H has eigenvalues 1 and 1. So the lambda for capital H is just 1. Okay. So whatever eigenvector you write, let's say I write a, b, any arbitrary vector, so it will correspond to lambda h equals 1. Okay. There is no other distinction. But you know that I have not specified the eigenvectors yet, because these are still arbitrary. These are kind of, I do have a rotational freedom in a 2D space. Okay. Then what you do is that you introduce an operator that commutes with H. In this case, you might like to use sigma 3. Okay. So sigma 3 is basically 1, 0, 0, minus 1. You can check that my sigma 3 and H, these two commute. Okay. So I know that the eigenstates of H will be eigenstates of sigma 3 also. I mean the non-degenerate eigenstate. So rather I should say the eigenstate of sigma 3 will be eigenstate of H also. Now I can be confident that the eigenstates of sigma 3 are basically 1, 0, that corresponds to eigenvalue plus 1, and 0, 1, that corresponds to eigenvalue minus 1. So this is the sigma 3 eigenvalue. So I am using my sigma 3 eigenvalues to label my degenerate eigenvectors of H. Okay, so that is a choice, that is an informed choice I am making, that my eigenvectors of H are not well defined for a set of degenerate eigenvalues, and I am taking the help of another operator that commutes with H, that means that is compatible with H, and I am using the eigenvalues of that particular operator to label my degenerate eigenvectors of capital H. So if I need to label the eigenvectors, so I would suggest, so I would label it as a 1, 0 is my eigenvector corresponding to 1 minus 1. That means that my Hamiltonian eigenvalue is 1 and my sigma 3 eigenvalue is minus 1, and this is again, sorry, this is plus 1 and this is minus 1. So you see the degeneracy is broken by the eigenvectors of that commuting observable. Okay. Now you will see that the same thing is being applied for hydrogen atom. So for that you have 3 quantum numbers, so n, l, m. So energy only cares about this n. Okay. You put a different linear combination of these L and M, and it will still be the eigenstate of my energy, right? So you usually write the the whole eigenvector or the wave function as psi n l m, right? So this is equivalent to your psi n l m. Okay, so here what m is doing, so m correspond to the eigenvector of the Lz operator. Okay, so since it has a rotational symmetry, and the rotation of generator, the generator of rotation is along z axis, about z axis is Lz, and since Lz commutes with H, okay, so since Lz commutes with H, I can use the eigenvalues of this Lz to label my degenerate eigenstates of H. Okay, so but the eigenvalues of Lz is just m times H cross, and that's why I use the labeling m. That's why if you have a central potential, then Lz always commutes with H, and that's why your energy eigenvalue never depends on m. It never depends on the azimuthal quantum number m, because this always holds no matter what is the structure of the potential. As long as it is central, as long as it depends on the magnitude of r, this always happens. Okay. Now, from where does the L degeneracy comes from, small L degeneracy? That has to do with your basically Laplace-Runge range vector. So since Vz is equals to 0, okay, so you see that there is an additional set of degeneracy, and this only happens for -1 by r potential. Remember, no other potential will give you this thing. Okay. So if you have a -1 by r potential, then only your Runge range vector will commute with the Hamiltonian. So by the same token that I told you that this leads to a degenerate eigenvector, this will also lead to a degenerate eigenvectors of H. And again, you will label those degenerate eigenstate by putting the labels of the eigenvectors of Vz, which would be like L. Okay. Now, not always the symmetry that transpire from these things are obvious. So, for example, the symmetry that corresponds to this commutation relation is obvious, because I know that the angular momentum generates a rotational symmetry. Now, and by the same token, you might ask that what does this Vz gives you? What kind of symmetry does it gives you? Now, this is also sort of a rotational symmetry, but in a complex plane. It's a bit difficult to visualize. If you want, so this actually gives you an SO4 symmetry. I mean, you don't have to know what this is for now, but just notice that for -1 by r potential, we have an enhanced symmetry, just not a rotational symmetry, but an enhanced symmetry that is not very apparent from like geometry, from the geometrical consideration. But if we actually delve deeper into Poisson bracket of the commutator relations, then I can discover say additional quantities that are conserved for attractive Coulomb potential or attractive gravitational potential, and that actually explains why my energy eigenvalues for hydrogen atom depends only on n, okay, and nothing else. So, and that is the reason of this degeneracy about L. Okay, so I will pause here for a moment and tell me if you have questions.
Hello, sir.
Yes.
Sir, apart from that Lz and Vz, there is another quantity L square also commutes with H. So
yes, but remember, you cannot use that. Because L square Lz, yes, but sorry, but you have already used that. So now, so Lz H equals to 0 is not the only thing. It's basically Lx H is also equals to 0, right? Like three of these things are all equals to 0. Okay, but they do not commute mutually. So Lx Ly is not equal to 0. Okay. Or Lz Lx is not equal to 0.
sorry,
So
my
when
connection got lost at that moment. Could you please repeat?
yeah, so when you have made up your mind that you will take Lz to be your, like you will take Lz to break the degeneracy along M, then these things you cannot use anymore. Okay, so that's why the L square doesn't give you a new thing. So it is like the choice here. So you choose sigma 3 to label these eigenvectors, right? But instead of sigma 3, you could have also chosen say sigma 2, which is 0 minus I 0, right?
Yes, sir.
And then your eigenvectors would have been 1 plus minus I. Okay, maybe 1 by root 2. Okay, so these are also eigenvectors of H. Okay, but this gives you so these are basically labeled by 1 and plus 1, but that is of sigma x or say sigma y. Okay. So but once you have made up your mind that you will use sigma 3 to label the things, then you do not have any other choice. Do you understand my point here? Because sigma x, sigma
both
y,
way it
sigma z are not mutually compatible.
Okay, sir.
Yes, say that again. Hello, are you saying something?
Yes, sir. I was saying that for every system, the energy if conserved, then we should have a conserved quantity, right? For suppose for harmonic oscillator, we have energy is conserved for a certain stationary state. Then what is the conserved quantity?
No, in a harmonic oscillator, in one-dimensional harmonic oscillator, there is no degeneration. There is no other conserved quantity. So all the eigenstates of like nothing commutes with that Hamiltonian.
Sir, last question. Sir, for that Laplace Rangelange vector, we get the Poisson bracket, we get Hamiltonian is 0. Then what is that conserved quantity from we can figure out?
That is the vector itself. Like in the same way that is, I said that Lz is a conserved quantity. The Vz
Okay,
is
sir.
also conserved quantity.
Okay. And if if we have a commutation relation L1 L2 is L3, and if I know from previous my calculation that L3 is conserved, then I can conclude that L1 L2 will be conserved too, or I have to check
No,
out.
if you, so remember, I said if L1, L2 were conserved, then L3 is conserved. You have
Okay,
just found
no
that only L3
backtracks.
is conserved.
Okay, sir.
Okay.
Okay, sir. Hmm.
Anything else? All right. So let me move on from this brief aspect of quantum mechanics. And there is one additional comment that I would like to make. That is again, I come back to so I remember I introduced you to something called F mu nu, and I called it the electromagnetic field tensor. Okay. And we sort of found it in a bottom-up approach. Okay. We did not give very good explanation, but we just found out that it gives us uh, like a convenient way of writing my Maxwell's equations. So like del mu F mu nu equals to 0. And it like the free Maxwell's equation. Yeah, that I am not assuming any sources, and this actually follows from a Lagrangian, which is -1/4 F mu nu. Okay, that's fine. You might not know this, but it is okay. Okay. Now I want to have a different look at this electromagnetic field tensor, like where does it comes from? Okay, so for that I will need two Poisson bracket relation. So one is that, so if you have a function of q and p, then you can check that just like in quantum mechanics, you take the Poisson bracket with the coordinate, and you get del f del pk. And if you take the Poisson bracket with momentum, then you have minus del f del qk. Okay, so you can check those. This should be very easy. Now, the Hamiltonian for an electromagnetic field, as or you, as many of you have already found out, is P minus QA whole square by y sem plus Q phi. Okay. Now you can think of it that the momentum has been replaced. It's like p square by twice m plus q phi, but where p is replaced by this thing, this quantity p minus qa, that I call the minimal substitution. So I can write this as summation over k pk by twice m, of course, okay, plus q phi. Okay, so I can treat it as kind of an ordinary thing with moving and with an electrostatic potential q phi, but momentum replaced by this thing. So where pk, capital Pk, would be given by small pk minus q times ak, the kth component here. Okay. So now I will call this thing, I will name this thing as my covariant momentum. Okay, for reasons that I will not explain now. Okay. So this is my covariant momentum. So, rather, let's say, just to not confuse with the covariant vectors that you learn in tensor, I will call it the gauge covariant momentum. And perhaps you will see the reasoning for this thing here. So now, if you, just for fun, if you take the Poisson bracket between two of these gauge covariant momentums, so this is your Pj, Pk. If you do that, then it is basically the Poisson bracket relation of, say, Pj minus Qaj and Pk minus Q times Ak. So since the commutator between Pj and Pk is 0 and Aj and Ak are 0 because they are all functions of coordinates, or they are totally of momentum only, then those are 0, and the non-zero term will be given by minus q times say Pj Ak plus Aj Pk. Okay. So remember this Aj or Ak, these are they are respectively the components of the vector potential, and the vector potential usually depends on coordinates. So again, by using this rule here, that Pk times F equals del F del Qk, so this thing becomes del Ak del Xj, and this becomes basically minus del Aj del Xk. Okay. So again, if you simplify Pj Pk, and that would be given by Q times del Aj del Xk minus del Ak del Xj. Now again, this is readily identifiable as your Fjk, right? So this is Q times Fjk. For now, I am not worrying about where to put the indices. I am using, say, Euclidean space, and it doesn't matter whether I am working with contravariant or covariant indices. Okay, but in general, I need to be very careful. But you get the general idea that if you take the Poisson bracket between two of these weird momentums that I called my covariant, my gauge covariant momentum, then what you get is usually the field strength tensor. Okay, at least the space part of the field strength tensor. So the time part, the temporal part, we could not derive because we are still stuck with non-relativistic classical mechanics, the non-relativistic version. So, and in general, it can be derived. The whole F mu nu can be derived. But the thing you notice is that this Fjk is invariant under a gauge transformation. So remember that f mu nu was del mu a nu minus del nu a mu, and the gauge transformation in 4 vector notation was given by, let's say, a mu goes to, like, a mu prime is just basically a mu plus del mu f. Okay, so if you now actually calculate that f prime mu nu, which is your del mu a nu prime minus del nu a mu prime, and you substitute this thing, then you will see that the extra term, this is just del nu f, this cancels out and it gives you back del mu a nu minus del nu a mu, which is just f mu nu. Okay, so f mu nu is a quantity that is not gauge sensitive, that does not depend on this what value of a mu prime do you choose. Okay, so remember, when you tried to do electrodynamics with vector potential, you always needed to mention what gauge are you working with, whether you are using Coulomb gauge or you are using Lorentz gauge. Okay, so you have to specify, because knowing the electric and magnetic field does not give you uniquely the information about the vector potential or the scalar potential. So you need to put in some extra information, like what gauge are you working in, and then only can you figure out your vector potential. But the advantages in working with this field tensor, this f mu nu, is that it doesn't matter in what gauge you are working with, whether you are working with a mu or you are working with a mu prime, f mu nu is a quantity that remains the same. Okay, so f mu nu is kind of, you may note that it is a gauge invariant quantity. It does not depend on gauge transformation. Okay, so the whole electrodynamics, the complete electrodynamics can be reverse engineered by demanding this. So the way we learned electrodynamics so far, probably by starting from Maxwell's equation, we did not question Maxwell's equation. So those came from experiments before Maxwell. So one piece given by Coulomb, one piece given by Biot-Savart. Many of them did experiments and came up with those intelligent laws. Maxwell's combined them, and then we discovered that there are some beautiful properties of the Maxwell's equation. One of the beautiful properties is that it is invariant under gauge transformation. So it is not sensitive to gauge transformation. Now, I can ask the question in an opposite direction. So I can ask, if I demand a theory involving a mu and a nu, such that the theory is gauge invariant, do I land on the Maxwell's equation? The answer is yes. You can basically do electrodynamics in this more abstract notation. You can start by demanding gauge invariance. You can start by demanding a theory. I want to write down a theory that is inherently invariant, inherently insensitive to such gauge transformation. Okay. Then what you get? Then you notice that this f mu nu should be a fundamental quantity. And since this f mu nu transfer from the commutation relation of these two momentum, okay, and the Poisson bracket of these two momentum, so these kind of tells you why we call this momentum as my gauge covariant momentum. Okay, so this generalized momentum corresponding to this is called the gauge covariant momentum. Okay, so that is it, I guess. Time is up. So now let me know if you have questions. By the way, are you now familiar with working with f mu nu? Yes, tell me first.
Sir, you go little up in the slides. Please
Yeah.
go up. In the Rungelen's vector part. Yes. Yes. Here you have written that v dot r equals to epsilon cos theta. Yes, I
Yes.
understood that V has a magnitude and epsilon, and it makes an angle theta with r hat. So the component along the r hat direction is epsilon cos theta. But how can you write that cos theta is similar to the cos theta of the orbital equation of the central potential or central force, that L by
Oh,
r equals to 1 plus epsilon cos theta?
yeah, it is the same. So this theta is basically the so basically you are orienting your V along the Z axis. That's it. So V is a constant vector, right?
Yes.
So you have freedom to orient your Z axis along any of the direction you want. Okay.
Oh, okay,
Before
okay,
you,
okay.
so you orient your Z axis along V, and that's it.
Okay, sir. Understood.
Okay. Anything else? Have you been introduced to FMU New yet from your electrodynamics course? Are you
No,
working
sir.
with? Not yet. Okay. All right, then I would suggest that you should self-study these things. At least people who are thinking about doing theoretical physics, you should self-study this. Yeah, classical electrodynamics in your. Which book are you following? You are following J.D. Jackson's book. Okay, then the book should contain these things. Anyways, it should not be my idea to speak on, but these are very interesting things. You can, yeah, you should look into more detail. I mean, it would give you a better understanding of what the gauge transformations really are, and it will give you an idea why photon is massless. That is because of the gauge symmetry. You will understand that. You can try to understand why photon is massless just from this. One step further from this, and you will understand why gauge symmetry renders photons massless. All right, then I will close this session now. I will stop recording.